Alright everyone, welcome back to Brazil 2015-3. So we have a problem that's like, it's basically like a fake derivative is what's happening. You have this integer n and it's false derivative. False derivative is defined by pretending that you're using the power rule or whatever. And anyways, the problem is to prove that there's infinitely many n such that like f of n is f to the n minus 1 plus 1. So NT-construct problem. Because this artificial derivative function is so... It's pretty artificial, I'll say. I don't think there's like a really good natural interpretation for it. So I suspect that I'm going to be looking at like some very specific numbers. For example, well, I guess my sentiment is probably like one of these n minus 1 or n is going to be like a power of prime power? A multiple of prime power? I'm not sure. Actually, here's sort of the core problem, which is that freshman's derivative. The sophomore stream is true though. Something. Yeah, I feel like I don't know for any. Are there n for which I have good control of like an n minus 1, like the prime factorizations? I want to say not really. Like, when do I have the property that like two numbers differ by 1 and I know their prime factorizations pretty well? It's not very often, right? Or, what if n is a square? Yeah, I actually thought, if you... square free? Oh, what happens if it's square free? Is it just like equal to... Oh, if it's square free, it's equal to the exponents. Okay. Fine, that's fair. Yeah. Oh, actually, if n is square free, then the derivative... Okay, so that's probably worth knowing. If n is square free, then fn is literally 1. It's given exactly by 1. Okay, what would it take for it to equal to... Okay, that's never gonna work. Yeah, on the other hand, the square free... Okay, I am less scared than I was before. Because I was looking at this as like, oh my god, these values are really bad. But actually, as long as like n and n minus 1 are like square free-ish, yeah, most of the prime factors won't matter. So I feel like maybe all I need to do is find like... let me think this through. Can someone give me like a single example of n? Problem suggestions happened at the start of the stream, and then we wasted 2 hours on just puzzles. Oh my god. Prove that limit of x to 0, x to the x is 1. For Warren, it's probably better if you write it as e to the x log x. Then you just want to show x log x approaches 0 as x to 0. Which should be true. Yeah, that should be true. Okay, I feel like I want a base which is like a single example of a number that is Okay, let me just compute some values. So f of like 3 squared is equal to 6. I need two like consecutive numbers that are like, pretty composite. Like 8, well 8 and 9 work. F of 2 to the 4 is 16. Ah, crap. I was hoping it'd be equal to... F of 2 to the cubed is equal to 12. I just need one example. No, or not even one example. I want two numbers with f values that are off by 1 from each other, and I'll explain why in a moment. Oh man, alright, I need a 5, 5, 4, 16, 15. F16, is that all 16? Oh no, it's 32. Sorry, might be. Someone give me two numbers that differ by the right amount. Okay, 13 and 27 work. Yeah, I had the same thought. Wait, does 13 help? Wait, I don't think the 13 doesn't work, right? Oh, it's f of 13 squared. Yeah, but I agree. So here's the idea. I'll write out the idea that I have, which is that suppose A and B are fixed coprime integers with f of A equals f of B plus 1. I don't even care if A and B are adjacent. Then what I'm going to do is I'm going to hope that there are a lot of solutions where n is 0 mod A. Well, n is 0 mod A, n is 1 mod B, and also n over A is square free. And n minus 1 over B is square free. And I guess I also want like GCD of A with n over A to be 1. So this is vaguely the idea I want. It's like, if this is true, then I can get things to work pretty well. So 169 you're telling me is the 3q. No, 13 squared gets you 26, but f of 27 is like, no, 27 doesn't work, right? Oh, it's 26 and 27. Ah, okay, great. So the key integers I want are 13 and 27. Okay, because 13 squared. Here. Let me just write this. So 27 is. Okay, so this idea I think will probably work out. Alright, let's see. Okay, so the claim is that, what conditions I want? I want 3 to not divide x. I need 13 to not divide y. I need x square free. And if so, then this is true. Right? Because f of 169 is 26 and 27. Okay, so here's the fact that you may or may not know. Prob rel 1. Let me make sure. Sorry, never mind. That's not a fact. So here, the claim is that if x and y satisfy if x, y are square free with x not divisible by 3 and digit not divisible by y, then this will work. So we got the two numbers that I was trying to fight for. Actually, now that I think about it, it shouldn't have been that hard to get those numbers. 13 times 2. Oh man, I'm really bad at arithmetic. I just needed two adjacent composite numbers. Claim. So if this, then okay, cool. And then I mess up my LaTeX. So if 3 doesn't divide x and 13 doesn't divide y, and x and y square free, then f of 27 is, yeah, that's true. So we can now parameterize this. So if I want 27x minus 169y equals 1, this is equivalent to saying like x equals 169m plus some modular inverse, and y is equal to 27n plus some modular inverse. 3VT says it's 4 and 25, which, or 25 and 4, which sounds right. But it shouldn't really matter what values they are. Like the point is that because the 27 and 169 are relatively coprime, yeah, there should be something. Wait, did this go the right way? Is it for 675? I think it's minus. I think I need to be minus. Yeah, I think it should be minus. Anyways, yeah, if you do minus, then it's fine. So like 144 and 23 should be okay. Yeah, that button. Yeah, this is definitely an empty construct problem because it's like, you know, we're not interested in finding all things. We're just interested in like having most of them work. Okay, so this will work. We can throw in factors of 3 if we want to make sure they're not divisible by 13. So we can do like 27 times 39m and this. Yeah. So I'm gonna just throw in these factors of 39, and when I do that, it will ensure that I'm not worried about this number being divisible by 3. Okay, so all that's left to do is show this infinitely many m for which both of these numbers are relatively prime, or are both square free. And this should work because the sum of... Okay, so fix a large integer n and consider choices of m, capital M between 1 and large M. So the intuition behind what I'm going to do is that how many integers are square free? About 6 over pi squared or something like that is roughly the intuition. So for each prime p, the number of m which it kills off is at most twice. So for every prime p, let's say p less than m, because if no, we'll just do oh crap, no, it's okay. Ceiling of m over p times 2, p squared times 2 is what happens. So for example, like some of these will be divisible by 4, for example, and that's okay. Oh, 4 is actually really annoying. All right, change the plan. We're going to make these even as well. 78. So p at least 5. So for example, like some of these will fail because the x for y will be divisible by 25. But how many of them have that property? You either need x to be divisible by 25, which happens about 4% of the time, or you need y to be divisible by 25, which also happens about 4% of the time. So together, it's about 8% of the time is the intuition. And formally, the expression is this. And this is less than, we'll bound it above in the following way. It's at most the sum of, across all primes p, of m times 1 over p squared, well, sorry, 2m, plus the sum of There's an error term which is called the number of primes less than capital M. And this is this, let's say this sum is p at least 5. Oh no, where did I put the, oh. Okay, I probably put the square in the wrong place, p squared. Alright, so the number of primes less than m is like, this is on the order of m over log m. So for large enough m, this will eventually go away. Isn't the ceiling as stated infinite? Good point. Sorry, let's fix that. Let's so p equals 5 to... Is it enough to do it from 5 to m? No, sorry. I need to go all the way up to... So how big do these numbers get? They are all less than like 20,000 m. So let's just do that. 20,000 capital M. That's the largest that any prime that's bigger than 20,000 m will not divide either x or y. Actually, I can... It's actually p squared, so I can go up to like root 20,000 m or something. But basically, like, you don't actually use every prime. Like, if the prime is larger than the numbers involved, then you don't care. I can probably improve this to like square root, like, okay, it takes no extra work. Square root 20,000 m. So the number of primes is, so here I don't need the prime number theorem anymore actually, but the prime number theorem would have told me this Euler term is root m over log m. Like, this is just the number of primes. And this is sum. And this, the exact value of the zeta function or whatever, like the sum of 1 over p squared, is a lot less than 1/2. So this will always be less than 0.99 m eventually for large enough m. And therefore, there will always be little m's for which both of these numbers are, both x and y are square free. You take these x and y, throw them in here, bada bing, bada boom, everything works. And we're done! Alright. Anti-construct, definitely. Alright, any questions? What is this estimation magic? It's not magical, it's just like, not that many numbers, your intuition should be that the number of square-free integers is quote-unquote, whatever... Actually, I don't know what the... Sorry, let me get what the number is. Wolfram Alpha... .com. Yes, you helped. Oops. No. Okay, no, go away. I don't need chessboards anymore. Sum p squared, p to the minus 2. I'm actually curious what the value is, just because it does matter for this proof. It's not hard to, I think for us it's not too hard to bound. But, oh, come on. Hello. Yeah, I agree. I was just curious what the actual value is, but it looks like Wolfram Alpha really doesn't want to tell me. Lame. Alright, I give up. Just put sum 1 over p squared. Does that work? No, that sums over everything. Okay, sum, square, reciprocal, prime, numbers. Primes, okay, so it's not a... Okay, it's not a known value. On the other hand, it's, yeah. So we needed it to be less than 1/2 after I removed, like, the even and multiples of 3. So that's more than good enough, yeah. Okay, but, sorry. To answer the question, whoever for the motivation is like, basically, your intuition should be that, more than half of numbers are square free, is what that page says. Like, more than half the time, if I pick a uniformly random number from 1 through n, that number will be square free, because the squares of the primes are just not dense enough. So that's why when I see this and I'm like, oh, well, I want 2 numbers to be square free. Well, if they're quote unquote independent, then probably like a quarter of the time it will work. And you can't, they're not actually independent is the issue, but the bound is so weak that we can actually bound the probability of A and B by P of A plus P of B. So probability of bad X plus probability of bad Y is still good enough for us. So you write it down and then you're like, okay, deal with the error term, blah, blah, blah. Error term doesn't matter. We're fine. Yeah, the sum is like 0.17, so this sum is really small. The reason I remember this sum is because the very last USUMO problem I did in high school, I needed an estimate for this sum as well. I think I needed it to be less than like 1. Which problem is this? The problem I was referring to is USUMO 2014-6. Which is basically like, if you have a bunch of numbers such that a plus I and b plus j have a common factor, then you get some bound on a and b. And basically what happens is the reason you get a bound on a and b is because you get like an n by n grid, right, of common factors, and then each prime can only show up so many times. So a lot of the primes in that table have to be really big, is the TLDR for that problem. But yeah. Thanks for 27 and 169. I don't know how long it would have taken me to find those, but it probably would have been a while knowing me. Is it just me or USUMO 2022 intimidating? Depends on who you ask. I thought it was... I honestly thought that problem was a little scary, but, you know. You try all small primes, realize it's all even. Yeah, you need an odd cube. I see. Yeah, but 27's the ticket.